All right, so we got a frictionless wedge here. It is in equilibrium. What is theta 3?
What's the angle on the pulley? Should we know that?
Oh, at the top? No.
Okay.
That would tell it. Now, even though have drawn this angle and it kind of looks like a 90-degree angle, please don't assume that it is. I just sketched something up and I put the labels down. This is not necessarily drawn to scale. I've given problems like this on a test, and some people said, oh, let's just assume that's 90 degrees, so, oh, that's easy. Yeah, it's not a geometry problem, it's a physics problem.
That's fine.
What's the process?
Facades method. Hold on. You have to use the facades method. And
Yeah.
then
So what's the first thing you do?
force diagram.
Yes.
What does it say at the top?
That's a mu. This is to indicate that it's frictionless. That's mu sub k and mu sub s are equal to 0.
Oh.
This is supposed to be a mu sub k, but it got mangled, so that's
Oh.
why I rewrote it.
Okay.
Should we know which one's going up and which one's going down?
No.
Okay, we'll find that out.
It's frictionless and in equilibrium, so
Oh, okay.
it doesn't really matter if they're moving or not. It could be dynamic equilibrium or static equilibrium. It doesn't change the answer.
Alright.
We bring friction into it, then it matters. All right, so theta. Force diagram. So yes, we have the wedge, we have the pulley, which is part of the wedge. We've got the ground, we've got the rope. But really, what we care about are these two masses here. Since the rope is ideal, it's going to be the same tension throughout. It's frictionless. Pulley's not turning. We don't have to worry about any of that stuff. These are the two things we do worry about. So what are the forces acting on?
So there's normal force that's pointing upward from the right side of the 3 and left side of the 5, and then downward to the ground, perpendicular to them.
The way, I think you would probably draw it correctly, but the way you worded it
Yeah,
was
I'm not really
odd.
wording it.
When you say up, I'm thinking this way.
Oh, I was thinking of this way for 3, 5
Okay.
for this one.
All right, so I got a normal force going this way on 3, and this way on 5.
And then downward in the opposite direction from their normal forces towards the ground.
Yeah, if we were doing force diagram of the ground also,
Oh, okay,
then
so we're
yes,
just doing the about, okay.
we're just. And nothing wrong with you doing that, just these are the two that I really care about.
Okay.
So there are indeed other parts of this pair is pointing onto the wedge, going that way. Yep, which way acting on what?
Well, the 5 would have it pointing this way, and the 3 would have it this way.
Okay.
And then we have gravitational force going the opposite directions from the normal forces.
Rookie mistake.
Really?
What'd you say?
Oh wait, no, it's supposed to be pointing just straight downward.
Yes.
Forgot.
Weight, yeah, weight always points,
Right.
for the small object, always points down.
Okay, no,
What do you mean a small object?
Not planet sized.
Oh, okay.
Okay.
Well, can't we just go ahead and put like W cosine theta, W sine theta?
Sure.
Okay.
Why don't we just go ahead and label this as theta 5. You could just put 40 degrees in there if you want to write that down, but. All right, so we break that up. Oh, well, actually, acceleration?
Uh,
That's the next after force diagram is the acceleration.
well, since that's frictionless, couldn't it go either it's in equilibrium.
So if it's equilibrium, acceleration is zero.
Yep.
Oh,
So when you set up the coordinate system for something in equilibrium, I mean, typically you want the coordinate system set up so that one of the coordinate vectors is in the direction of the acceleration.
so just.
But in this case, acceleration is 0. So I would recommend be consistent whichever way you're gonna go.
Okay.
So just imagine in your head, it's either gonna go like this or like that.
Okay.
And it doesn't matter which one you pick.
I'll go from left to right.
Go ahead, so it's going this way?
Yeah.
All right, so we've got a coordinate system there, we call this I3 hat, J3, and then I5 hat, J5 hat. So that's force, acceleration, coordinate axes, decomposition. Now we get into breaking it up.
Wait.
Which part is down the ramp? Sine or cosine?
Hold on.
Oh, down the ramp?
Can you dumb question, can you re-say why the 3 I hat J hat is like this and the 5 I hat J hat is like this?
All right, just from a math convenience point of view, it's helpful that if you imagine it's going like this, so that they're in the direction of motion.
Oh, okay, yeah, got it.
You could have easily picked the other way, and mathematically, since acceleration is 0, you could have them both pointing that way, but maybe it's a me thing. It feels more coordinated that way,
So,
and will be more helpful later on.
cosine would either be on the side of tension or the opposite side of tension. I don't know which way though.
On the side of tension, over here.
Yeah, or the other. I'm not sure.
The weight is acting down.
Yeah.
So when I break it up,
It should
there'd
go-
be a component this way, that.
Okay, so cosine is supposed to be the opposite of tension, and then sine.
Sine's down the ramp.
Hold on.
And then
Oh.
cosine.
So you two disagree.
Oh yeah, she's right.
Yeah.
I figured that.
Sine's like,
Don't get bullied into that.
No, I just looked at my picture.
we're working together.
Yeah, it's like a
Don't bully.
partner group.
All right, did you have a question?
No, I agree with, I agree. I
Do you
concur
wanna
with.
wonder how they were raised? Think you're good? Looks like we're all good with this. So I have normal force this way. I have W5 cosine of theta 5 into the ramp, or towards the ramp, W5 sine of theta 5 down the ramp. Tension going this way, and then over here, W3 sine theta 3 down the ramp. W3 cosine theta 3 in towards the ramp. Y3 FT.
So sort of equilibrium, the tension's the same, FT.
Because it's an ideal rope, the tension's the same.
Oh, okay.
If it were not an ideal rope, then if it had friction, we'd have to bring the pulley into it, because the pulley potentially will start to turn now, we have to take that into account.
Okay,
That's chapter 9.
okay.
If we added a mass to the rope, then you would have to know how much of the rope was on the right side and how much was on the left side of the pulley,
Added a mass to the rope?
if we added mass to the rope.
Oh, gave the actual rope. mass.
Yeah, we'll assume that the rope is massless, because that's a much more complicated problem.
Okay, that group.
What would the mass, how would the mass affect the problem?
You'd have an additional weight acting here and here. If it moved, then it does matter if it moves or not, because as it moves, if it's moving this way, then as time increases, you have more weight on this side,
Right,
and so the acceleration would not be constant.
okay, yeah, I get it.
That'd be kind of piece of cake.
Thanks.
And now we're looking at calculus.
No.
Well, that's what you guys do in 251.
Usually not it is fair game for 251, but we typically, there's too much stuff to cover in
Okay.
251, like in 151. All right, so we've broken it up, we've decomposed. What comes after decomposition?
Equations.
Equation.
How many equations will we have?
We will have four. Wait, yeah, four.
All right, let's do it.
So are all of the equations going to be set equal to zero since that we don't have acceleration? Okay.
Yes. All right, so I'll have an I5 hat, a J5 hat, an I3 hat, and a J3 hat. You know, just stick with the process right now, and on a test or quiz, if you can skip a step, go for it. Just make sure you know what you're doing. Give me one of them, somebody.
For I5,
Oh, yeah.
okay. For I5 hat is FT minus W5 sine theta 5 equals 0.
All right, someone else, new voice.
I have to think. Yeah, you're going so fast.
For J hat, it would be J hat 5.
J- okay.
5 hat, whatever. It would be, let's see, positives would be normal force 5 minus W5 cosine theta 5 equals 0.
And again, over here, it's equal to 0 because this is equal to mass times acceleration. But since acceleration is 0, equals 0.
You would tell us in a test if it's moving or not, right?
Well, whether it's moving or not is irrelevant to what we've done so far.
Because if it's not moving, then we'll know there's zero acceleration. That's what I'm trying to get at.
The acceleration can be 0 and it's moving. If it's moving at if each mass is moving at a constant velocity, then the acceleration is still 0.
So let me reword this. Will you tell us if acceleration is equal to 0? Or will we have to figure that out?
In the problem I said it was in equilibrium, so that's my way of telling
Okay.
you acceleration is 0.
Alright,
If I did not specify it was in equilibrium, then I would have to give you more information.
okay.
I got.
All right, Margaret?
I did, W sine theta 3 minus
Wait, which one are you doing?
I hat 3.
Okay, sorry, W3 sine theta 3?
Oh yeah, I forgot, sorry. W3 sine theta 3 minus FT equals 0.
And I do want to point out that they are equal to 0. These are equations. Equations need to have an equal sign or an inequality sign. If you just write that only, that is not an equation. Usually not an issue, but there are some students that, I don't know if it's just the excitement of doing physics or what it is, but some people just give an expression and not an equation. All right, one more to go. Let's see, we have two voices we haven't heard on this one yet.
Y3 minus W3 cosine theta 3 equals 0.
All right. What do we know? Let's see, we know. Let's do substitution and then let's do this bit.
So,
Sorry, I got ahead of myself.
Yeah, so weight is equal to mass times, oh my gosh, the G. Well,
Yeah. So I have Ft minus M5G sine theta 5 equals 0. Y5 minus M5G cosine theta 5 equals 0. M3G sine theta 3 minus Ft equals 0. Y3 minus M3G cosine theta 3 equals 0.
what's the G called again? What's the right?
Acceleration due to gravity.
Alright.
All right, now, what do we know? Let's see, we know mass, we know G, I'll specify planet in just a second. I know theta 5. I know M3, G. So I have 4 unknowns and 4 equations. My unknowns are the tension, Y5, Y3, and theta 3.
this is only for for the 5 kilogram mass, but the friction, no, the tension for the 5 kilogram mass is the first equation. If we just move it to the side, does that make sense?
Just move it to the side.
Just okay, so just move
Maybe
like the
solve for
side.
FT.
Yeah, so like just
Well, we could,
just like solve FT by like solving the sine theta times mass times gravity, acceleration through gravity, and then add that to the other side, so FT is equal to the sine theta times that. And then we could just plug that in for the rest. Would that be correct?
Yeah. So that's 5 times 9.8 times the sine of, I think I said 40 degrees. Looking back briefly, yeah, 40 degrees.
Times 9.8.
32.76.
31.5 if you want to.
31.5?
Yeah.
Okay, but, so, for the other I hat, we also could do the same thing, so is this where it would be important to label FT for like which block it's for? 'Cause-
No, because it's the same, because it's an ideal rope and pulley, the tension is the same throughout that rope. So the tension at each end is the same.
So it will be true then that I3, or I hat 3, the, M3G sine theta 3 will also equal that number.
Yes,
So so that's just one way to solve it.
so that's gonna be equal to 3, as Laura provided, times the sine of theta 3. Our two J hat equations don't really come into play here because we don't have friction. But
wait, I got lost right there.
of this,
Yeah,
we got FT to be 31.5.
right.
Those are the same tensions. So the tension is also equal to M3G sine theta 3.
Okay. I'm with So, are we,
The original question was to find the unknown angle, right?
Yes,
So we just
finding theta 3.
So
we just
so,
solve for
What
let's
if we
solve for
set
theta.
mg sine theta 3 equal to m3 g's, or g sine theta 5? Then solve for the angle.
Wait, say that again?
Can we set the mass, or m5 g sine theta 5 equal to m3 g sine theta 3?
Yes,
we could,
there's no.
and you'd save yourself a little bit of time because the G's would cancel out. But what do we end up with for sine theta 3?
So we divide 31.5 by 3 times 9.8, and then we use the sine, the arc sine to find it. Okay. Keep getting an error.
Dude,
I have an error as an answer.
yeah, what else get an error?
What were you saying? Oh,
9.8. Okay, well, we have to, hold on, let me try.
I got,
31.5
I don't know.
divided by 29.4.
Alright, so let's get a new page here.
Arc sine.
So if I take the first and third equation here. On the first equation, I have the tension equals M5G sine theta 5. And from the third equation, I get tension is equal to M3G sine theta 3. These two are therefore equal to each other. So M3G sine theta 3. G's would cancel out. We're solving for theta 3 here, so sine of theta 3 is equal to M5 over M3 sine theta 5. So theta 3 is the arc sine of M5 over M3 sine theta 5. Is that too fast?
What was the angle
Alright. it sounded, you're good with this?
This
Setting them
makes
equal,
sense.
yes,
Okay,
and then I get taking out G, and then,
this is what we're trying to find, that's the problem.
Right.
Okay,
why
So-
couldn't we do it from the equation we just had?
you could,
Okay,
yeah, so in the equation we just had, we kept G in it. So this would be the arc sine of M5G sine theta 5 over M3G. This is 31.4, which is what we had before. This is 3 times 9.8.
So, no matter which way we do it on our calculator, this way or still including G, it gives us an error.
So two of you have errors.
Yeah.
wait, you plugged in for theta 3 right now?
To solve for theta 3, yeah.
Oh, no, I